let's start with the new section, 2.7, analyzing graphs of functions and piecewise functions. All right, we're very talkative today. Does anyone know what symmetry means? Is your face symmetric? Ish, right? So if I cover half my face and you see an eyeball over here, there's probably one over there too. Okay, that's symmetry from the center. And so that's the idea. Only instead of eyeballs, we have points. If I have a point over here and symmetric with respect to the y-axis, I say, what is that distance from the center? On the other side, I must have an eyeball also the same distance away. Are we okay with this definition? Okay, does that work for every point? This point, same distance on the other side. This point is 5 away from the center. So 5 away from the center on the other side, we have symmetry. Why do we care about symmetry? It turns out if you have to graph and you know it's symmetric, once you've plotted half the points, you know what the other half will look like. So it's going to save us a lot of work in the future. We'd really like to identify symmetry. All right, that's symmetric with respect to the y-axis. What about symmetry with respect to the x-axis? So now we have this dividing line in the middle. And if we have a point that is about 3 away up top, it should be how far away on the bottom? 3 away. Okay, any questions about this? Let's do a tricky one. Let's say symmetry with respect to a point. Let's talk about the origin to the origin. And the origin is the point 0, 0. It turns out a point like 2, 4 becomes -2, -4. If I draw a line through the origin, I say, what is this distance? I want the same distance on the other side of the origin. XY becomes -x, -y. Does that work for all these points? What about 4, 0? On the other side, we go through the origin. This is distance of 4 away. 4 away on the other side is another point. And this is true for every point on our graph. Kind of crazy to think of symmetry about a point instead of a line. All right, so let's say I graphed half my function, and I say that my function is symmetric about the x-axis. Can you draw the other half? What would that look like, my entire graph, if I drew? Yeah, so I have a point here that's 2 away. On the other side, I have a point that's 2 away. I have this point that goes to that point, and so we have a circle. Okay, so I'll call this part A. I used an incorrect word there. I said a function because this doesn't pass the vertical line test. It's just a relation, not a function. Part B, sketch a graph that's symmetric with respect to the y-axis. So look at the original. What would that look like if we reflect it about the y-axis? I might plot this point and say it's 2 away from the y-axis. On the other side, we reflect it over here. And the point 4 is 4 away from the y-axis. So on the other side, it's 4 away. And the point here is 0 away. It stays 0 away. This one would be a function. So this is part B. All right, what about, could you graph something that's symmetric with respect to the origin? With respect to origin. So this point here is how far away from the origin. So on the other side would have to be equally as far away. All right, this point over here is how far away from the origin. We need something equally far away. This point here has a distance from the origin, and we want something equally far away. So we get the bottom half of the circle over here, part C. Any questions about this? Another way to think of it is you're rotating it about the origin 180 degrees. Yeah, that's true. You could think of this as a double reflection. Or that. So across the origin could be thought of as a double reflection.
We got any points?
Yeah, if you don't get it yet, then you can do more points, certainly. Okay, test for symmetry. What if I don't have the graph? How can I tell if my function has symmetry? Because I want to graph it and I want to cut my work in half. So symmetric with respect to the x-axis, you replace a y with a negative y, and it yields the same equation. Okay, symmetric with respect to the y-axis. What does this notation mean to you? So what order pair does this correspond to? F of negative x. What order pair does that correspond to? Negative x is plugged in, and f of negative x is the y value. What about on this side? What does this mean? X is plugged in, and the y value is f of x. So what does it mean that f of negative x is equal to f of x? It means if I plug in x or negative x, I have the same y value. Does this idea make sense to you? So if I have a point over here, I'll call it x comma f of x. If I plug in, so this corresponds to an x value. If I plug in the negative x value, equidistant on the other side, it's telling me I get the same y value. Negative x, f of negative x. So if that's true for all x values, it's true for my entire function. And I have symmetry with respect to y-axis. Are there any questions about this? The other one's slightly more tricky, and that is, if I plug in negative x, it's the same thing as if I make the whole function negative. So the y value will be the same. So if I plug in x, I will get the negative y value. What this is saying is they have opposite x values and they have opposite y values. This is what type of symmetry? With respect to the origin. If I have a graph, if I have a point, x, negative f of x, I'll have one on the opposite side of the origin. So whatever that distance is, I have equidistant on the other side. I have a point called negative x, f of negative x. So opposite x and opposite y values. So if it's symmetric with respect to the y-axis, a vocab word, we call this an even function. Because it normally happens to things like parabolas, right, of degree 2, like x squared. So we often call it an even function. Symmetric with respect to the origin, we call that an odd function. Because these often happen to things like cubics with odd powers, but not always. I'm going to come back to example 2, but right now I just want to find out, is my function even, odd, or neither? Let's do example 3, part B. No, let's do part A. I'm going to call this f of x. Actually, can I? Is this a function or is it just a relation? If it's solved for, if y is solved for, and I don't have a plus or minus in the radical, it's usually means it's a function. Or just about always. Okay, so in this case, what we do is we just plug in negative x. And we see, what do we get? Square root of 3 minus negative x squared. And when you square negative x, what do you get? Yeah, positive. The negative goes away. So we get square root of 3 minus x squared. Maybe I should say in blue, this becomes x squared. Okay, and then you can compare this to the original function. How does this compare to the original? It's the same. So does that mean it's even, odd, or neither? So if I plug in negative x into my function and I get the original function back, it's even. So that means whether the x and y are positive or negative, I get the same y value. It has the same height, so it's symmetric about the y-axis. We say f of x is even, which means the symmetry is with respect to the y-axis. Are you okay with me using WRT with respect to? All right, any questions about that? Yes. To the original. If it's equal to the original function.
No, that you put fx. You're saying if it's equal, like y equals with no positives and negatives, then it's fx.
If my result after I simplify, this is my result after I simplified f of negative x. And I compared that to the original.
Yeah.
And it's the same.
I
Okay.
totally did that one. Wait.
Should we try the next one?
Oh, never mind. She answered it.
Okay. For the next one, we do the same thing to test if it's even or odd. You plug in what? We plug in negative x, and we want to see, do I get the original function back or the negative of the original function? I plug that in, and we simplify. Negative x cubed over negative x in parentheses squared plus 1. Please use parentheses when you plug in negative x. If you don't, it will come out wrong usually. Okay, negative x in parentheses cubed. Do I get negative or positive? That is correct. Negative x cubed after we simplify. What about the negative x in parentheses squared? Positive x squared. Okay, did I get the original function back? It's definitely not equal to k of x. Because this has a negative sign, this does not. So that means what? It's not even. It doesn't mean it's automatically odd. What do we need to check? What are we comparing it to? We said, is it k of x or is it negative k of x? Negative k of x is equal to x cubed over x squared plus 1. Are these the same? If the negative's in the middle or the negative's on top, it's the same. Yes, they are the same, which means that because these are equal, in fact, k of x is an odd function. So it is symmetric with respect to what? Yes, the origin. Let's try part C. I want to see if it's even, odd, or neither. F of, we plug in negative x, is equal to negative x in parentheses squared plus 4 times negative x in parentheses plus 8. So negative x in parentheses squared becomes positive x squared. Negative x times 4 is negative 4x. Plus 8 remains the same. Okay, is this equal to the original? No, this is different. Negative 4x plus 4x is different, so it's not equal to f of x, which tells me what? Not even. It's not symmetric with respect to the y-axis. What's a parabola? Are all parabolas not symmetric with respect to y-axis? I guess it could be shifted over, right? Then we need to compare it to negative f of x would be negative in parentheses x squared plus 4x plus 8. So if we distribute the negative, we get negative x squared minus 4x minus 8. Is that equal to what we just computed? Are these the same? No, they're not the same, which means what? Okay, so let me just write, this is not equal to, yeah, it's neither. Negative, or sorry, f of negative x. So it's not odd. Is it neither or neither? Neither? Okay, I'll believe you. Any questions about this? So we just memorized maybe some mathematical operations. Let's try to go back and reflect what it means. So the first one, I plugged in negative x and I plugged in positive x. And I say they're always the same. The y value is always the same no matter what. So on the either side, is it either? Either. So x and negative x, right, equidistant, we say it has the same height. And that's what it means to be symmetric about the y-axis. So that's what we did in part A. We showed symmetric about the y-axis. We plugged in x and negative x and got the same y value. Any questions about that? So the next one, we plugged in x and negative x, and we got opposite y values. And that's the definition of odd. Well, let's do part E. One more for good luck. Is it even, odd, or neither? G of negative x is equal to -2 times negative x to the fourth plus 5 times absolute value of. So negative x to the fourth power does what? Yeah, so we get -2 remains the same, but becomes a positive x to the fourth. And the absolute value of negative x is the same thing as the absolute value of positive x. So we say this is equal to the original, which implies even. Metric with respect to the y-axis. Any questions about that? All right, so slightly different is example 2. We want to find, is it symmetric with respect to x-axis, y-axis, or origin? And in this case, we may not have functions. Because what does it mean to be symmetric with respect to x-axis? It means it looks the same above as below. And so why are these not necessarily functions? Fails the vertical line test. Relations that are symmetric with respect to x-axis are not functions. So I can't have this f of x formula necessarily. Okay, so how do I test these? Let's test symmetric with respect to the x-axis first. These would have the same x value or y value. We're going to plug in negative y for the y value. So I'm going to have x is equal to absolute value of negative y minus 2, and the absolute value of negative y, x is equal to absolute value of y minus 2. Because these are the same, it is in fact symmetric with respect to the x-axis. Okay, how do we check if it's symmetric with respect to the y-axis? We plug in negative x for x. So in this case, we would say negative x is equal to absolute value of y minus 2. Are these the same equation? They're not the same. Maybe it's better to solve for x. X is equal to negative absolute value of y plus 2. So I multiply both sides by negative 1. It's easier to see they're not the same. They're the opposite sign. So no, we're not symmetric with respect to the y-axis. What about symmetric with respect to the origin? We're going to plug in negative x and negative y and see if we get the original equation. So in this case, we have negative x is equal to absolute value of negative y minus 2. So negative x is equal to absolute value of y minus 2, which is not the same as the original. X equals absolute value y minus 2. Therefore, it is not symmetric with respect to the origin. Okay, so let's try this one more time with this problem. If I plug in, let's see, symmetric with respect to the y-axis. How do we check that? Plug in negative x. So in this case, we'll say negative x in parentheses squared plus y squared is equal to 9. And we get x squared plus y squared is equal to 9. Is that the same as the original? Same, yes. So our function or our relation is symmetric with respect to the y-axis. All right, the next one. Is it symmetric with respect to the x-axis? You plug in negative y, and we have here x squared plus negative y squared. And we simplify x squared plus y squared is equal to 9. Is that the same as original? Yes, same, which means it is symmetric with respect to x-axis. Then we try the origin. Is it symmetric with respect to the origin? We plug in negative x and negative y. Negative x in parentheses squared plus negative y in parentheses squared plus 9 equals 9. My apologies. Is that equal to the original? Same as the original, which means, yes, it's symmetric with respect to the origin also. Does that make sense based on what the graph of that function looks like? Sorry, that relation. It's a circle centered at 0, 0. So yeah, that has all kinds of symmetry, right? All right, let's move on to another concept. A piecewise function. Are you familiar with these? Yeah, it turns out one function isn't good enough to represent reality sometimes. We might need multiple functions. For instance, when you're accelerating from 0 to 45 miles per hour in the first 20 seconds, we could say that this line represents your speed. And this function looks like y is equal to 2.25x. But if I graph that line, it would go up forever. And that doesn't map reality because at some point, I stop accelerating, right? And I level out at 45 miles per hour, in which case my function becomes a constant, y equals 45. Then after 80 seconds, or after 60 more seconds, I start decelerating or braking at a constant deceleration, and my graph looks like this function. So a piecewise function is how we can represent, for instance, 3 functions on the same graph for different domains. So what these domains represent, 0 to 20, is saying everything between these 2 lines. Those are the x values between 0 and 20. What does my graph look like? The next domain from 20 to 80, what's my graph look like? And from 80 and on, what does my graph look like? So we want to represent it in this form because we might not have the graph in front of us. So the way we do that is we say that for the x values from between 0 and 20, my function looks like this line. However, if my x value is between 20 seconds and 80 seconds, I'm going to constant 45 miles per hour, so y equals 45. And after 80 seconds, between 80 seconds and 110 seconds, I'm decelerating, so I have negative slope, but my function looks like this line. Are there any questions about this? Yes.
I have a question.
Okay. No, this is just asking you to understand this notation. So when it asks you, for example, what is f of negative 3? We have to ask ourselves, which domain are we in? Are we less than or equal to negative 2, between negative 1 and 2, or greater than or equal to 2? On my graph on the right, you can see here at negative 3, you can see which function it is. What I want you to do is take out this x value, x equals negative 3, and say, is it in my first interval, my second, or my third? In this case, is it true that negative 3 is less than or equal to negative 2? Yes, it is true. So that means f of negative 3 looks like the top function is equal to negative x minus 1, and I plug in -3 for x? My answer is 3 minus 1 is 2. Any questions about that? So f of -1, what does my function look like? The downward line, the constant line, or the square root? I take x is equal to -1, and I say, is that less than or equal to -2? No. Is it greater than or equal to -1? Yes. In fact, x equals -1 does satisfy this inequality where it is greater than or equal to -1 and it is less than 2. My function, f of -1, should look like this function here. It's -3. It's constant, -3. In the next interval, f of 2, in this case, x is equal to 2, is that in the first, second, or third intervals, 2 is greater than or equal to 2. It's in the third interval. What does my function look like when I plug 2 in? The square root of x minus 2. Yes, 2 minus 2. The square root of 0 is 0. Any questions about that? Finally, 6 is in which of my intervals? X equals 6 is in fact greater than or equal to 2, so it's in the third. So f of 6 is equal to square root of 6 minus 2. Square root of 4 is 2. Any questions about this? Yes. The graph is a visual representation of the piecewise function. Right, so let's talk about how we interpret that for right now. So if I want to graph this, which we're going to do next, so please pay attention. I first look at my first interval. X is less than or equal to -2. I find, no, that is not it, is it? This should be a -1. Please correct these notes here. These should match up with each other. Okay, so this should be corrected to -1. But -3, luckily, is still less than or equal to -1. Okay, so I want to look first at my domain, x less than or equal to -1. Here's x equal to -1. So what does it mean for x to be less than -1? It means that we're on this side to the left of that line, x equals -1. Are there any questions about that? This represents x less than or equal to -1. In that region, our graph looks like -x minus 1. It looks like this line, -x minus 1. Y-intercept is -1, and slope is down 1, right 1, down 1, right 1. But I erase everything on the right of x equals -1. My next domain, I say when x is between -1 and 2, so I'm between these two, I'm in this region. What does my graph look like? Y equals -3 is a horizontal line. But I erase it everywhere outside of the region that we're talking about. Lastly, we have x greater than or equal to 2 is this region to the right of 2. It looks like the square root function shifted right 2. And this is the square root function shifted right 2. We don't have to erase any of it because it doesn't exist to the left anyway. Any questions about this? Yes. What's absolute value of x? Okay, f of x is equal to absolute value of x. Is that what we're saying? Does it? I'm gonna have to look. Right. When x is to left of 3, right of 3, it looks like this line. Okay, well, we're gonna practice that right now with this problem. So let's graph this. I look at my graph. I should draw these better. All right, and then I look at my domain. X is -1 is a very important point. So I'm going to find that here, -1, and I'm going to split my graph here. When it's less than -1, am I talking about the left or the right side of this line? To the left, because these are my x values, and these are values positive that are greater. I want the ones that are less, like -2, -3, -4. Okay, so to the left of this line, I want my graph to look like what? This function. Y equals x plus 3 when x is less than -1. So it's really talking about this side of the line. So I graph that function. 1, 2, 3. So my y-intercept is 3. And I have a slope of 1, so I go up 1, right 1. Up 1, right 1. On the opposite side, I go down 1, left 1. Down 1, left 1. Down 1, left 1. I drew the line y equals x plus 3. But I only want it to exist to the left of x equals -1. So I need to erase it to the right. I'm going to erase it to the right of here. Maybe I'll just keep it as a dashed line so we see that it used to exist over there, but it doesn't. Last thing, on the red line, do I put a solid dot or an open dot? If x is less than -1, we're not including it. And there's a open dot there. All right, the next interval, x is between what and what? -1 and 2. So I look between -1 and 2, and my graph looks like what in this region? A parabola, x squared. I draw that parabola. Whoops, this should be 2, 4, right? 2, 4. And I draw it on this side. And on the left, on the red line, do I draw a closed dot or an open dot? Can it equal x equals -1? Yes, so it's a closed dot because it can equal it. On the right side, do I use an open dot? Open, closed. And that's the graph of our piecewise function. And then I erase all these other lines. Any questions about that? So it looks like a line to the left of -1. Looks like a parabola between -1 and 2. All right, we have a few definitions, and we'll classify a function. So a turning point is just when you go from decreasing to increasing. So decreasing to increasing, that's a turning point. Increasing to decreasing, this is another turning point. Can you identify turning points? They're the peaks and valleys of our graph, right? Absolute minimum is the lowest point. This graph has no absolute minimum because it goes down forever. It has no absolute maximum because it goes up forever. But relative min is the lowest point in a region. So this is what we call a relative min, because if I look to the left, a little bit to the left, the points are higher. If I look a little to the right, points are higher. Therefore, it is a relative minimum, even though the graph goes lower somewhere else. Exactly. So these valleys are relative mins. So this is another relative min, right? And what's a relative max? The peaks. Relative max. The definition of increasing and decreasing just means it goes higher from left to right. That's all I really care about. So this one's increasing because it's going higher left to right. This one's decreasing because it's going lower. And constant, it stays the same height. So I want to at least do this example. When it says where is it increasing, it's talking about the x values, that interval. So my function is increasing only here. It's going up here, right? So what are those x values? 2 to 3, we do not include them, because at that point, it's not increasing or decreasing, it's unknown. So it's always parentheses. Where's my function decreasing? Okay, so my x value, starting x value is -4 all the way to -1. It's also decreasing over here, which would be what? 3, 2, yeah, and forever. Okay, so these are x values only. So I'm talking about these x values here and these x values here. What's that? No, we always use parentheses because at that point, we don't know. It starts to exist here, so we don't include it. Where is it constant? And these x values here, whoops, from -1 to 2. So note that these are all intervals. Intervals of x values. Do we have any local relative maximum? We have a peak here, right? Because a little bit to the left, the points are smaller, and a little bit to the right, the points are smaller. So this is a, what is that ordered pair? 3, 0. So this is a ordered pair, not interval. Please be careful about confusing these. I'm not saying 3 to 0. Yes. What's that? Yes, that's really interesting, huh? What about -4, 4? This one, it depends how the book defines it. Different books define it differently. If we're saying our domain is all real numbers, we would say no. But if we say our domain's -4 to infinity, we'd say yes. So that's a really good one to point out. -4, 4. I don't think you'll have one like this. I think your homework doesn't include it. So I'm hesitant to say don't include that. One last statement. Relative min, there is none, because a point here, if you look to the left and right, it's not the lowest point, it's the same height. So these don't actually count as relative min.